So it's really a pleasure and an honor to introduce Professor Latha Venkataraman for today's public lecture, which is titled Scaling of Electronic Devices from the Vacuum to a Single Molecule Diode, or she also may be talking about a general class of single molecule circuits. So Latha is, you'll be happy to know, is a homegrown Bangalorean kid. She actually graduated from the Valley School in Bangalore, and then moved to pursue her bachelor's degree in physics from MIT. And then once she finished her coursework there and earned the degree, she went on to do her PhD in physics with Charles Lieber, who is absolutely a leader in nanotechnological applications and devices with different kinds of applications. After finishing with her work with Charles Lieber's lab in Charles Lieber's lab, she went on to do a slightly different detour from what regular academicians are used to at this level after finishing PhD. If you're still interested in academics, you really want to do a postdoc. But she went on to join a company, Whiterun Corporation, where she was for 4 years as a research scientist. But I think something called her back in some level when she joined back in Columbia as a research scientist, and quickly rose amongst all the academicians in Columbia due to fundamental experiments that she did during the time of 2003 to 2007, and she became an assistant professor at Columbia. Latha's group has been doing very pioneering experiments on electron transfer, basically electron flow through molecules in between two electrode junctions. So creating these molecular interfaces between two electrodes, that could be metal electrodes, she can actually look at how molecules can actually conduct charges once electron is injected from one of the source electrodes. So the fundamental experiments that she did involved hanging a single molecule in between two metal electrodes. And what she did was, although the ideas existed, but she created a very clean system, a clean experiment that could basically measure these currents between the two electrodes when the molecule is bound in between. Because of these very, very phenomenologically interesting and exciting experiments, Latha has won numerous awards. NSF Career Award, she was awarded the NSF Career Award, the Packard Fellowship, and she's also an Alfred P. Sloan Fellow in the United States. I just wanted to mention this, that she's truly an inspiration for all of us, and especially for all of you who have come from a college in Bangalore, that to see that one of you could also follow the similar footsteps as Latha is doing some very inspiring experiments, which is at the forefront of what science and technology can be, what is pushing it for. So, with those words, I would like to invite Latha to deliver her talk.
There's a small memento from ICTS we want to give before.
Thank you. So I grew up in Bangalore and went to high school here, as Professor JD told you all. And I'm going to tell you about some experiments that we do and also motivate why we do it in a very indirect way. But most of all, I would like you to take away some interesting message. And so if you have questions, please ask me in the middle of the talk. That's completely fine. I don't want to necessarily finish my whole talk and then have you all bored just sitting and listening. And maybe if no one asks me questions, I will start asking you questions and then you will have to answer. So why do we do this single molecule work? I need to make sure that I don't move my head relative to the mic. So just to give you an overview of how things have shrunk in the electronics industry, you can think about the first computer. This was called the ENIAC. Whoops. I need to get used to this pointer. Okay, the ENIAC. And this was actually a really huge machine. And most of you are aware that computers have got faster and smaller. The scale of this was, I don't know, a few rooms. What was interesting was that it was developed, around 69 years ago, roughly the age of my mother. And it used vacuum tubes. So how do vacuum tubes work? Vacuum tube works by heating up a piece of metal and then applying a voltage between the hot piece of metal and another metal and getting electrons to flow only in one direction. And so vacuum tubes was really the technology that pushed all of these early computers. And the size of a vacuum tube was actually huge. And so to make things smaller, just using the same technology of making a diode with a vacuum tube was actually quite hard. And here is sort of the next generation computer that was designed. This is UNIVAC from 1951, and then things got more complicated. But the first big transition that was made was to go from using a vacuum tube as a diode, and a diode is basically something that allows current to flow only in one direction. They started to use something called a transistor. And I'll get into what a transistor is in a little bit. And using a transistor really allowed things to be shrunk down. And so in 1982, when I was at the Valley School and the first computers came out, this was the computer that I used for the very first time. And we tried to play a game of chess with this computer, and we made a move, and then we had to wait overnight for the computer to make its move before we could continue playing. So it was extremely slow, but it had at least shrunk to the size that you could hold on a table. And now things are extremely small, and all of this scaling has really happened because the basic building block in a chip in a computer has actually become smaller and smaller. Okay, and so what I'm going to tell you is about how that building block has become smaller. And so this building block, the transistor, is really the driving force for scaling of electronics. And the first transistor was developed by Bell Labs also in 1946, so as old as the first ENIAC computer. And its size was ½ inch. And the people who actually made this transistor, again, it's really something that allows current to flow one way and not the other. So what allowed these, when they made the first transistor, they didn't realize how it would be useful. They had just done something that was fundamentally interesting for them. And then if you go to 1958, this is the first integrated circuit. So it uses a bunch of transistors, and they're put together on this glass slide-like thing over here. So it's actually pretty big. And then following that, things started to get smaller and smaller rather quickly. And so by 2010, Intel had developed something called the Core i7 chip, which is about 1 centimeter by centimeter in size. And this is an image of the inside of this chip. And this had 1 billion transistors. So by this time, the length scale of a transistor has shrunk down to be about 100 nanometers in size. Okay, so we have come from something that's ½ an inch or 1 centimeter to something that's 1 billionth of a meter in size. So shrinking by many orders of magnitude. Okay, but then you can say, okay, how small can I get, right? And so this is the main question. How small can I make something that's basically a switch? And you can make it as small as maybe 1 atom or a few atoms. You can't go much beyond that, right? And so IBM is already making transistors that have the smallest dimension, that is 7 nanometers. And the size, what is the size of an atom? Does anyone have an idea? Since no one has asked me a question, I'm asking you a question. So someone other than the conference participants, do you know the size of an atom in any unit? Nobody? An angstrom. Very good. So you're in the right length scale. It's depending on which atom that you're talking about. If it's hydrogen, then it's about an angstrom. If it's gold, maybe it's about 3 angstroms or so, okay? And so an angstrom is, 10 angstroms make a nanometer. So IBM is making a device that's 70 angstroms. It's basically 70 atoms, 70 hydrogen atoms in size. So now if you think about how much more small can I get, I can't go much smaller. I can't go a factor of 1,000 or a factor of millions smaller than what IBM is already doing, okay? And so to think that you can use molecules to make switches is maybe getting more into science fiction at this point. In any case, we are still interested in how to make such devices, and more importantly, how does electricity flow through something that's so small, okay? And so in my lab, we actually designed and built a switch which was made with a single molecule. And this is 1 nanometer in size, so basically 10 angstroms. And this is something that goes on and off by mechanically pushing across the molecule, and the molecule is attached to 2 pieces of gold metal. And then we pass current through, and I will explain exactly how we do experiments like this. But the length scale going from what IBM is doing in a mass-produced way to what we do in our lab, which is really 1 device at a time, is not very far off, okay? So the amount of shrinking that can be done now is actually quite limited, but what we are after is, how things work in that length scale. Okay, so just to push this effect of scaling to see, how much things have scaled, you want to put it in perspective. So I have this little cartoon that I stole from one of my mentors, Forrest Stormer, who got the Nobel Prize for the quantum Hall effect. So what he said was, if you take a transistor and you see how much it has scaled down between 1946 and 2015, you can write some metrics for this, right? The weight has decreased by a factor of a trillion. This is an approximation. The speed has increased by a factor of 1,000,000. Most important, the cost. I can buy this laptop and bring it with me, whereas that big machine, ENIAC, there's no chance that an individual could own such a machine. So the cost has decreased by a factor of 1,000,000, okay? And these are all round numbers. This is something that I just wrote down very quickly. It may not be exactly accurate, but it gives you a right order of magnitude. Now, what you want to think about is another object that existed in 1946 and exists now, and we can apply the same scaling to just tell you how dramatic this is. And so we're going to take a car, and this is a car from 1946, and this is a car from 2016. And if you want to apply all of these scaling, and especially the cost scaling to the car, a car would weigh, only 1 gram. That's how much things have become smaller. So if you scale the weight of a transistor over all these years and you apply the same scaling to a car, the car today should weigh only 1 gram, right? That's incredible. The speed should be, this is miles per hour, because this is something for an American audience. I should have changed it to kilometers per hour for this talk, but I forgot. But anyway, it's 60 million miles per hour is how much faster the cars would have to go if you apply, again, the same scaling between 1946 and today. And the cost, the cost of the car, if you take the cost of the car in 1946 and scale it the same way the cost of a transistor has decreased, a car should cost $1 today. So this type of scaling is just incredible. And this is what the integrated circuits industry has achieved. I think they have done marvelously well. And so what we are not trying to compete with them, we're more interested in understanding how things work. And so I'm going to end my introduction with this slide, and then I'll go into details of my experiments by putting a photo of Feynman. And he basically motivated everybody to say, by saying that, there's more room in the bottom, so you should dig into the small scale. My husband, who's an astronomer, will not agree with this, but the things that we are after is how things work as you go smaller and smaller and smaller, and this is what is exciting for us. And so molecular electronics as a post-CMOS technology, so something that Intel or IBM can use, is not what we are after, and it's not sort of my big motivation for science. It's basically to take the physics of how things work at the single molecule level and then understand it and have fun with the experiments that we do. And today what I will tell you is really a detail that has to do with something that can work only in these molecular systems, and that's a quantum mechanical effect, and it has to do with quantum interference. So the bulk of my talk will explain that to you. But I just want to say our main goal is really to understand fundamental science at the nanometer scale. Okay, so let me give you, I've given you a lot of motivation. So why do we do this? There's also the fun idea that if you are working in a chemistry lab and you make a little molecule in your test tube, and then you say, since I don't work in a chemistry lab, I don't know exactly if you even use test tubes anymore. But you can imagine that in one test tube you make a switch, in another test tube you make a LED, in another test tube you make a transistor, and then you somehow make your circuits with these molecules. This idea of getting functionality, getting different functions from just doing chemistry in a test tube is actually one of the major motivations of why we are studying such devices. So I'm actually going to skip that main part and focus on from now on, I'll tell you about how we do our experiments, and hopefully I can give you a flavor of what we are doing, and maybe you don't understand all the details, but you will at least hopefully get some of these messages. So for today, I'm actually going to tell you about how we use quantum interference effects through molecular designs and how that impacts the functioning of a single molecule device to make a device that goes on through quantum interference effects, or it goes off again because of quantum interference effects. And so what we're going to probe is a purely quantum mechanical aspect of how current flows through a single molecule circuit. And what I'm going to do is tell you how we manipulate these single molecules attached to electrodes and measure not only the current that goes through it, but also the forces required to break these bonds. Okay? So let me tell you what is quantum interference and what is interference as a starting point. And so all of you know that if you take a stone and throw it on a very still lake, you start to make waves on the surface of the water, right? So you're all familiar with water as a wave. When water is behaving as a wave, the water molecules are just basically going up and down at each point on the surface, but this wave seems like it's traveling far away, right? There's also light that behaves as a wave. Light also behaves as a particle. You can describe it in two different ways. But electrons and even molecules actually can behave both as a particle and as a wave. And so what are typical wave-like behaviors for water? If you put one stone in one place and another stone in another place, you see circles coming out, but when the circle starts to meet, you get funny behavior. And there are parts of the water where the water will not move at all. And there are parts of the water where the water will move at a much higher amplitude, okay? So basically, if I take a wave and I pass it through a slit, so this is a standard diffraction experiment, what you get is a series of waves. And here I have color-coded everything. So orange is high and green is low. So this is the high point. This is a low point. And you can also imagine as if you dropped a stone right there and then you have these waves coming out on the water, right? So now if I put another wall and then it has two slits over here, what happens, I'm going to have waves coming out of this slit and waves coming out of that slit. So that's like my two-stone experiment. And so I have this two-stone experiment. And now you can look at this carefully. And if you see that orange adds with orange, that means at that point, the wave has a much higher amplitude. But then there are places where orange adds on top of green. So one wave is wanting to move the water up. The other wave is wanting to move the water down. And there's no motion of the water, right? And so if I put a screen, or I somehow measure the height of the water oscillation, I'm going to see points where the water is oscillating a lot and points where there's no oscillation. And so how you can define these points is if the path length from my two spots is equal, then I'm going to have a maximum amplitude. And if the path lengths differ by exactly half a wavelength, the wavelength is basically the distance between these two peaks or the two troughs, then I'm going to have no amplitude of movement of water, right? And so this is how waves behave. Waves interfere, and then you add the waves, and then you figure out the amplitudes. And even though you have two waves coming and they're both wanting to make the water move up and down, if they don't add at the same time, then you're going to not have an increase in the amplitude. You're going to have complete interference. And so this concept is called interference. You're interfering your two waves. And you're going to have this constructive interference at this point, destructive interference at the other point. And so, and this is something that's characteristic of anything that is a wave. So what do we want to do? What we want to do is use the fact that electron is what current is made of, is actually waves as well as a particle, but electrons are waves. We want to flow electrons through a single molecule device and then test whether somehow I can make a molecular device with two paths in it, and then test whether I have this, when the paths are equal, I get constructive interference, and when the paths are exactly off by half a wavelength, I get destructive interference. So this is our goal. And so what we're going to do is look for molecular circuits and try and see whether we can find interference effects in our molecular circuits. And this way we can have molecules that don't conduct at all due to interference and molecules that conduct due to constructive interference. So what do we need to see, and how do we see interference in single molecule circuits? So first of all, these are the parts of my molecular circuit. I have my molecule, I have my metal contacts, and then I have a current meter, so an ammeter of some sort, and then I have a battery to supply the voltage so that it flows current through my circuit. And so how do we see interference? So first of all, we need a source of wave, and electrons are going to be our source of wave. We need two circuit paths, and this molecule conveniently has two circuit paths because this molecule has one set of atoms that are on the top and another set of atoms that go in the bottom. So I have two ways for my electrons to flow. And then I can change, transport is ballistic, this is a detail, that I can change the shape of my molecule so that I make one path longer than the other, and then I can see whether I have destructive or constructive interference. And the key part to note is that I need to have one path that is longer than the other by exactly half a wavelength, okay? Okay, so now we have to ask, how do we measure molecular, how do I put a molecule between two electrodes? And so what we're going to do is rely on the work of many other people, and the way they do make measurements at the single molecule level is through a break junction experiment. And so the idea is you take a gold wire and then you break it with molecules all around the gold wire, and then you can trap a molecule between your two electrodes. And this idea dates back to the work of Mark Reed and Jim Thor, and since then many others have done this type of work. I will flash a few and then highlight the one that I'm going to talk about in detail. This is an STM-Break junction system, and again I'll explain this in detail and tell you that there's a few other ways to do molecular measurements, but the break junction method is really the one that is most easy to work with. And so how does this work in our lab? So what we have is an STM setup. And our STM setup is actually pretty small. An STM is a scanning tunneling microscope. It can actually image atoms on a surface, not using light, because light cannot image things that are the size of an angstrom, but using measuring currents. And so we use this STM setup. It has a wire and then a substrate. And what we do, and this is a zoom in on the tip, this is a gold wire and a gold substrate. So we're going to try and form our single molecule circuit right in the gap between the tip wire and the substrate. And the way we're going to do this measurement is actually first smash the tip wire into the substrate and then pull it out like that. And what happens when you pull it out, gold behaves like chewing gum. So, you know, when you pull it out, it gets thinner and thinner and thinner and thinner. But it gets thinner to the size of a single atom. So the diameter of my gold wire right before it breaks from the substrate is basically a single atom in diameter. Okay, so about 3 angstroms. And then you can break it. And if you do this breaking in a solution where you have molecules all over the place, a molecule can happily go in there and bridge this gap between the two electrodes. And now I have created my single molecule circuit, okay? And so what we do is we measure conductance. So, I'll get into the details of what we measure. Let me just go on to the experimental details a little more. So this is what our gold substrates look like. This is, we evaporate a thin layer of gold on a piece of mica. And then we mount our substrate into our STM. We mount the tip into our STM. And then we cut the tip wire at an angle to make it sharp. Yeah. Yes. So the way we minimize the number of molecules, actually the geometry of the tip is pretty sharp, and the substrate is also very sharp. So if you imagine if I had 2 flat gold substrates and I was doing this, I would have the likelihood of seeing multiple molecules being quite high. But because I have these 2 very sharp tips, there aren't that many positions, so multiple molecules could fit. So we do see sometimes a signature of 2 and maybe 3 at the most. Okay, so once we put everything on the setup, then we have to add the solution of our molecule on this gold surface, okay? Because remember, we are going to break the gold in the solution of molecules. And we can use funky molecules. Some of them have a nice color, the solution. You put a solution on the substrate with a syringe like that, and then you take your substrate and you put it into the STM setup. And so this is what a measurement looks like in normal. You start your computer program, and the program just simply drives the tip in and pulls it out, drives it in, pulls it out. And then we do this thousands of times. And when we're doing that, we measure current. Remember, I have an ammeter to measure current, and I'm applying a voltage so I can I have a current flowing through my circuit. And so I measure conductance, which is current divided by voltage, in these funny units of 2e squared over h, where E is the charge on the electron and h is Planck's constant, okay? So what you notice is that at 10 to the power 0, which is 1, you have a plateau there, so you have the conductance. You're measuring the conductance of a single atom contact, okay? And that's really the signature of forming a single atom contact between the tip and the substrate, the fact that you see exactly 1 times 2e squared over h of conductance. And then once that gold contact breaks, you see here there's another feature, and this is a molecular feature, okay? So that means our molecule is attached between the tip and the substrate, and I'm measuring the current through that circuit, and then I divide current divided by voltage. I convert it to units of 2e squared over h, and I get 10 to the minus 2 to 10 to the minus 3. Okay, so all of this was for one trace. And I can go back and analyze my trace just because I collect thousands and I want to see what is the average current or conductance for one of those particular features. And so, whoops, okay, so here I'm showing you data on the gold contact, right? So this is my 2-atom contact, has almost 2 units of 2e squared over h conductance. My 1-atom contact has 1 unit of 2e squared over h conductance. And then I break this contact. So now you might ask, why is it that I see this, first of all, this flat plateau? So as I pull out my wire, my single atom contact, the conductance doesn't change. And if you ask yourself, why is conductance not changing with length? You have to go back to the basics of how electrons are flowing through this contact, okay? So if I take a macroscopic conductor, so this wire that connects, my microphone to this battery or whatever, in all of these wires, the longer the wire gets, the more resistive it is. And that's what Ohm's law tells me. So Ohm's law tells me that the resistance, which is voltage divided by current, scales as the length of the wire. The longer the wire, the more resistive it is, the lower the conductance. However, and that's because electrons that are going through these bulk, millimeter-sized wires, the electrons are bouncing around. And so the more length they have to cover, the more they bounce around and the more they scatter. And then there's loss and there's heating, etc. And so this is diffusive transport. When we go to the single atom contact regime, we no longer have diffusive transport. And what we have is ballistic transport. So as soon as the electron enters, it doesn't communicate with anything within the wire. It basically just zooms right out. Okay, so there's no scattering. Nothing happens to that electron except that it comes straight out. And so no matter how long you make the wire, it really doesn't matter. The length is not controlling the conductance. The conductance is really controlled by the nature of the atom that I have over there. So if I have gold, I have 2e squared over h, and if I have lead, I have something else, okay? Yeah. This is all room temperature. Everything that I will say today is room temperature. And so gold, because on the periodic table, it has a 1s electron, a 6s electron in the outer shell. There's exactly 1 electron that's participating in transport for the gold atom, and that's why we get 2e squared over h, okay? So if I had somehow a platinum atom or something else that had more electrons in the outer shell, I could see 2 units of 2e squared over h or 4, depending on what atom I have. Okay, so the fact that gold thins out like this into a single atom contact is not something that I'm telling you after I have seen it myself. We only measure conductance. So we can't see what we are measuring. We can only interpret based on the measurements that we do, right? But there's a group in Japan that actually put their entire STM setup inside a transmission electron microscope. And then they were actually viewing how the gold thins out into this chewing gum-like fashion into a single atom contact. And they actually saw that exactly when you have 2e squared over h of conductance, you have a single atom bridging your tip and the substrate. And so based on these past works, I can actually be sure that a 2e squared over h conductance tells me that I have the single atom contact. And just to show you how good ballistic transport is, so ballistic transport, remember, there's no scattering. My electron just goes straight through. And if there's no scattering, there's no mechanism for heating of my wire, right? So if I have a copper wire and I pass more and more current through it, it starts to get hot. Whereas if I have ballistic transport, there'll be no heating. And so if you look at the current density going through this single atom contact, it is 10 to the 13 amps per meter squared. So this is a huge number, and you can never get this high a current density through a a regular copper wire or even a gold wire, because there will be scattering. Scattering will cause heating, and then the whole thing will melt. So the fact that we have these really high current densities has to do with the mode by which electrons go across, and it's all ballistic transport. And that's what you need in order to see the wave nature of the electron. And I have to have this ballistic transport so that all the information that's in my wave doesn't get lost by the time it transmits across my device. So if you imagine that I'm passing water, and the water is going as a nice wave, but then there's all these rocks everywhere, then the waves are going to bounce off the rocks, and then I'm going to have a complete mess, right? So if I want to see interference effects, I need to have really a still system, and I don't want scattering of my wave across any object. Okay, so what do we do with this data? Because I'm also analyzing thousands of measurements, I need to show you how we do this. So we take our conductance trace, and then we count how many data points we have. We divide up this conductance segments into little bins, and as you can see here, there are many bins that have one count. We convert this entire trace into a histogram, okay? And then once we do the histogram, we take the next trace, make a histogram, and then we add it, and we keep adding subsequent traces. And so now I have a histogram of 1,000 traces of just gold, clean gold measurements, and you can see there's a peak at 1 times 2e squared over h, or g naught, and this tells me I always, or very frequently, form my single atom contact when I pull out my gold tip from my gold substrate, okay? And you can look at this on a logarithmic scale. So the other thing we can do with this data is also retain the distance information. So how long can I pull on a single atom contact before it breaks, right? And so the way I do that is I align my trace at 0 where it breaks from one gold atom to nothing. And then I add the next trace like that. I keep adding traces, and I make a 2-dimensional plot. And this 2-dimensional plot tells me that I can pull on a single atom contact for about 2 angstroms before that contact breaks. And what is pulling for the 2 angstroms is my gold structure is rearranging. The atoms are moving within my, my device, and then I see this plateau here. Okay, so this is sort of, yeah.
The rest of the sample, or you just take differences or something?
You mean, why does my axis not go all the way to?
Yeah, I mean, the rest of your lead probably also has some.
So the resistance of a gold wire, the resistance of our circuit outside. So just to put it in perspective, 2e squared over h is 12 kilo ohms. Our circuit, our entire circuit is about 20 ohms. And so it doesn't matter. Okay, so this is again on a logarithmic scale, just to show you that after I break my gold contact, there's very little data that I care about if I don't have molecules. Now remember, I'm going to do this in a solution of molecules. I'm going to break my gold contact with molecules, and I'm hoping my molecules will bridge the contact, okay? So let's look at data with a molecule. So this is a simple molecule, benzene diamine. And you want to focus on the paths. It has 2 pathways, and the 2 pathways are equal, right? And so I can, this is the data for the gold contact. This is the data after I break the gold contact. And you see all these features which were not there in the clean gold data. And this is a histogram of all the data that I have. The blue is 10,000 measurements with the molecule. And the orange is the gold measurement without molecule. So now you can clearly see that there's a peak at 1 G naught and 2 G naught. This is my gold structure. And then after I break the gold structure and the gold only measurement, there's nothing. But in my molecular measurement, there's this extra peak, right? So that tells me that I'm forming these single molecule circuits. I'm passing current through the single molecule circuit. I can fit the peak, and then I get a conductance of the single molecule device. So again, this is 10 to the minus 3 quantum, so this is about a mega ohm, okay? So it's a big resistance. A mega ohm is a pretty big resistance. Compared to my gold contact, which is 12 kilo ohms, I've gone down by a considerable amount, okay? Transport is still ballistic. Even though I have a big resistance, it's still ballistic transport because the electron that enters my molecule goes through without interacting with the molecule. Okay, and you can look at the same data on a two-dimensional plot, and what you see is really that the molecular junction can be extended only 1 angstrom. So somehow the molecular junction breaks very quickly, and we have an explanation for this, but I don't want to focus on these kinds of details here. And just to show you an illustration of how the junction can reorganize during this pulling experiment, this is a density functional theory calculation that shows the evolution of one particular structure, although in our experiments we measure thousands of these. This is just one example. Okay, so what I'm going to skip this part. Sorry about this. Yeah, so I'm going to skip. I think okay, so now I'm going to focus on my main story, which is this quantum interference effect. And again, we're going to compare measurements of a benzene ring with 2 pathways, and then we're going to see what happens when we go to the other pathway. Okay, and so we're going to measure these 2 molecules. This is the one I've already shown you data for. You saw this nice peak. We're going to compare it with this molecule in light green here. And this one is going to connect to a gold electrode here and there. And we're going to see that this pathway is longer than that pathway, and we want to know what happens. What conductance do we expect for that? Okay, so this is the data I've already shown you for the 1,4 benzene diamine. We see a nice peak. Does anyone want to guess what we see for the green one? Anyone want to guess? The same or more conducting or less conducting? These are your 3 options. Anyone guesses that it's going to be the same? Nobody. So is it going to be no conductance? Okay, so no one's going to answer. Then I will just, I have one answer from here, and we'll have to go with the director's guess. So actually what happens is we don't see anything. Now, this is a big problem. If you're doing experimental anything and you see nothing, if you're a theorist and you see nothing, it's fine. It's never a problem. If you're an experimentalist and you see nothing, you have to explain why you see nothing, right? There's many reasons why I see nothing. The first reason I could think of is, oh, this molecule didn't dissolve in my solution, and so it never could form a junction. Reason 1. Reason 2, it formed a junction, but somehow because the 2 arms are this funny angle as opposed to nicely vertically apart, it could only bind to one electrode and not the other. Because if you look at my diagram, I sort of need my molecule to fit in this funny sideway position, right? So maybe it never fits that way. It just doesn't work. Somehow it never gets in, right? The other possibility is this length is too short, and therefore it doesn't fit in my gap. So there's many reasons, except the interference reason. That's the other possibility, that there's interference, and therefore there is electrons going through. The 2 pathways interfere destructively with each other, and I have no current going across. That's the reason I want, but I cannot say just by looking at my null data that that's the explanation for the data. So you have to be very careful. And so we had this null result in 2005, and we just sat with it because we could not prove that this was a true quantum interference effect. And so null result is not conclusive if you're an experimentalist. If you see a 0 on your theorist, you can do very nice things with it. And so what we decided was we needed, yeah.
configuration is going to bind to the two ends of the...
Yeah, so I don't have control. And what I do, which is something I didn't stress, is put chemical anchor groups that bind specifically to gold. So in this particular molecule, it's only the two nitrogens will attach to the gold. And so that I have tested with many, many molecules, and I know that that's what happens. And therefore, I know that current will flow through this path, right? It's not going to attach here, yes.
To detect this, whatever,
Yeah.
wherever it's being measured, if
Yeah.
you were to move a little far from wherever you are measuring the thing, then it shouldn't be.
So I think your point is a good one, except at that point, I have to say my analogy with the water and the waves and all of that breaks down. Okay, so basically what you're saying is I'm measuring here and there. If I somehow move a little bit away, can I see the effect, right? And this interference is actually very fundamental to the structure of the benzene ring. And no matter if my gold is here or if my gold moves slightly away, if I'm bonded to that nitrogen, I will not see any interference. I will see destructive interference. Yeah, so if they're on adjacent, from chemistry, you know that you should see conductance. And we could not measure that one. That we saw nothing again. And that's exactly the point. If you see nothing, it's very hard to conclude that it's destructive interference. Okay, so what did we do? We decided, first of all, we know length is an issue. We cannot measure very short molecules, so let's go longer. So we designed these two molecules. So this one is two benzene rings, but both are connected in the nice opposite direction. In this one, I have one short pathway for each benzene ring, and then I have a long pathway for each benzene ring. So I've just basically doubled my system. And by making it longer, I make it easier for my measurements. So we designed these two molecules, and we're going to do something else. So measuring conductance and seeing zero is, again, not enough. It's a null result. So we need to prove that the molecule bridges this gap and we form a junction. And in order to do that, we have to measure a second property of our molecular junction. We can't just measure current. And so we have to verify that my gold is binding to the two sides and I see no current. Okay, so that's the goal over here. And so we need to, in order to do this, we're going to take, so that's what we're going to do with these two molecules. And I just want to convince you that, I told you this analogy breaks down, and then you might say, oh, maybe I'm just making all of this up, thinking about waves. And so what I can do is I can do a quick calculation for these two molecules, and I'm not going to go into the details of how we do the calculation. It's basically simply a tight binding calculation. And I plot here, it says transmission, think about it as conductance. And in the black is the conductance for this molecule that I expect to measure. And for the red one, because I have these two benzenes that I expect to see interference effects, I should see no conductance. So my quick and dirty theory work actually tells me that one should conduct but two not. Okay, so even though this wave analogy actually breaks down, this part is pretty accurate. Okay, so what are we going to do? We're going to measure forces, okay, and currents simultaneously. So that's our goal. And what are we going to do with measuring force? We're going to show that we break a bond between the molecule and the metal, yet we see no current through that molecular junction. So that's how we're going to get around the fact of this null result problem. Okay? And in order to do that, we have to transition to an atomic force microscope where we have a cantilever, and the cantilever is going to deflect, okay? So instead of my tipped wire that I showed you that smashes in and out of the substrate, I now have a cantilever which has a pyramid at the bottom, and this it's all gold, and it's going to go like this, back and forth between the substrate and the tip. And we're going to measure how much the cantilever deflects. So if you imagine a swimming pool with a diving board, right? So depending on how heavy you are and how much force you pull down the diving board with, the diving board is going to bend down, right? And so by measuring how much the diving board deflects, you can tell how much force is being applied on the diving board. And in the case of the diving board, it's your weight. In this case, the molecule is going to pull on this diving board, which is my cantilever, and I'm going to measure with a laser how much my diving board deflects or my cantilever deflects. And then that's going to allow me to measure how much force is required to break a bond in my junction. So the details of how this measurement works is basically the same. So I'm going to first show you conductance. My cantilever is going to smash into the gold, and then it's going to pull out. I'm going to see conductance plateaus, and then it's going to break. And then if I have a molecule, I'm going to see another molecular feature. This is a different molecule, so it has a different molecular conductance and a different plateau length. And this part is basically the same as what I already showed you. And then the force measurement, so now I'm overlaying force data on top of the conductance, so this is simultaneous measurement. And the force data, what does it tell me? It tells me when I have a plateau, I have a sawtooth. So my cantilever is bending down. As I pull on it, it's bending down. Suddenly the force gets too high, and then bonds break, cantilever moves up. Okay, that's what this is. The cantilever is bending down, although everything is reflected, it's bending. And then suddenly the force is too large, bonds break, cantilever drops down, and then I have repeated sawtooth pattern. And so once I break the contact between the surface and the gold, my cantilever is flat because nothing is pulling on it anymore. And so I have this force signature which is completely flat. And then I can do the same measurement with the molecule. Okay, so this is the force signature for the molecule. This is the molecular conductance plateau. And you see all these sawtooths again. So as the molecule is changing different positions between my tip and my surface, I see all these mechanical effects in my data. But then finally, when the molecular junction breaks, I have a flat signature. So nothing is holding my tip to my substrate. And then the tip is flat. Okay? And so what we are going to do, you see here we have conductance and we have force. So now we're going to compare the data for the interfering molecule and the non-interfering molecule. And for the interfering molecule, for the destructive interference, what do we expect? We expect to see force data, nice sawtooth pattern. If the molecule is there and pulling on my cantilever, I should see a force signature. But if there is no current, I should not see a conductance signature. And that will be my fingerprint. Okay, so so how do we analyze force data? So it's actually very straightforward. All you need to say is, F equals kx. We start with that. And so the force that I have, this is my sawtooth that I measure over here. My spring is stretching, and so linear increase force with distance. And then I have a rupture event. That's when the force drops down, my cantilever moves down, and that's my rupture force. Okay? So what we're going to look for is these sawtooth patterns in both molecular data sets. So you can also get the length of your molecular junction looking at the force data. Okay, so now I'm just going to show you my my molecule. So this is the no molecule measurement, just gold, right? I have a sawtooth pattern. I have a G0 plateau. Conductance goes to my noise floor of my instrument. The force shows this nice sawtooth. This is fine. Then I'm going to show this molecule 1. Molecule 1, remember, equal path lengths. I see conductance and force, right? I have have my conductance signature, simultaneous force, I have the step length, and now I have my molecule 2 data, and this is the aha moment that you should have. You see a force signature, right? I see the sawtooth, but I don't see a conductance. Conductance is going to the instrument mode. So what does this mean? This means that for 0.4 nanometers after my gold contact broke, I still had something holding my cantilever to my substrate. Otherwise, this should have been flat, right? And because I see the sawtooth, I know there's some little molecule pulling on my cantilever. And so I have a clear force signature, a clear step length, but no conductance. Okay, so now we can analyze all of our data, and I'm going to skip the details of how we do the analysis. But the first thing that we find, because both of these molecules have the same termination group, the bond that they make to gold is the same, we measure the same rupture force for both molecules. And we are only looking at the force data at this point. So both molecules bind to gold, both molecules break when the junction breaks, and the force required to break the junction is exactly the same. Both molecules have, you can measure a step length, and you see that molecule 2 has a shorter step length than molecule 1, which makes sense because remember, molecule 1 is diametrically opposite, whereas molecule 2 was slightly shorter. And finally, you can analyze the conductance data for all traces that have a force signature. And you see a nice conductance feature for molecule 1. This is the constructive interference molecule. If you look at the data for molecule 2, it's basically you see some tunneling in parallel, but there's no clear conductance peak in this thing. And so with this, I hope I have convinced you that by measuring two properties of these molecular junctions, I have shown you that you can use these purely quantum mechanical effects that you see at these molecular scale, which is something that IBM with their 7 nanometer device is probably not going to get to. So we've used a purely quantum mechanical aspect of current flow across a molecule to make one molecule that conducts and one molecule that doesn't due to quantum interference effects. And so I want to conclude, and hopefully I've shown you how we do some of these measurements, and you can see that we can measure multiple properties of these devices. And I should really thank the key person who built my AFM is actually also from Bangalore, interestingly. Sriharsha Aradhya, who's now doing a postdoc at Cornell, and Jeffrey Meissner from Colin Knuckles' group, who's my collaborator, who synthesized the molecules for us, and then funding and the ICTP for actually inviting me to give this talk here. Thank you for your attention. Yeah, that's the slight shift in topic that I decided as after I submitted the title for my talk. So this particular example is just to show you a fundamental property of a single molecule circuit. It's not going to work as a transistor. However, what you can imagine is a molecule that has two attachment points. One is diametrically opposite and one is removed. And then you can use quantum interference effects to either connect to one or the other and then make a transistor. And this was an idea proposed by a theory group probably 8 or 9 years ago.
A question.
Here. So what are the prospects with spintronic applications, molecular electronics? So let us say a simple magnet-magnet junctions with a molecule in between, a ferromagnet junction.
You mean for data storage or things like that? Or quantum computation?
No, a simple magnetic tunnel junction, for example.
So I think,
So let us say I have two ferromagnets.
yes,
So that's the simplest device that I can think of, connected via a molecule.
and your molecule is your spin filter or something like that.
Yeah, let's say there is a spin-dependent property with the molecule.
So I think people have measured this in the lab, but as far as I know, there have been no commercial applications yet. I'm actually a bit more on the skeptical side, so you might want to ask some more optimistic person about applications. I just think molecules might be more useful in cases where you can inject print your device and make large scale solar cells and things like that. And so to shrink down your spin sensitive system to distinguish spin up versus spin down at room temperature, which is where all of us are working, is quite a challenging task.
So when you showed this transmission of these two molecules, so at some energy the transmission is zero, right?
There.
So when you showed this, the transmission of these two molecules, at some energy the transmission is zero for one of the molecules. But if you change the Fermi energy of the leads, then I guess you get, that you can verify, is it?
Yes, so your interference is at Fermi if you're exactly in the middle of the gap. For this particular system, we are not far from the middle of the gap, so we still have 2 orders of magnitude difference in the conductance for the two. And this was a tight binding calculation that only includes the pi bands. Every molecule has pi and sigma. So sometimes the pi is shut, but the sigma can conduct, giving you conductance. So there's many reasons why you might see some conductance through a classical interfering molecule.
Yeah. So do we have any limitations for the size of the chain length? Like how big you can go and measure this one?
So our limitation is how much current we can measure.
Okay.
And so we can measure 10 picoamps pretty easily at the pulling speed that we are working at. And so you apply a higher and higher voltage in order to get the conductance down. But the length is really not the issue, more the current. So if you have a very highly conducting molecular chain, we have gone up to 4 nanometers. That's our current limit.
Suppose I don't apply any bias, but I have a temperature gradient.
Yes.
Like the tip of the STM tip is at a different temperature, the surface is a different temperature, and I want to measure the heat flux across. So will I encounter any...
Measuring the...
Yeah, I want to know whether I can use single molecule junctions to measure heat flux across single molecule junctions.
So to measure the heat is actually extremely challenging because there's many ways that... So the nice thing about measuring current is that if I have no molecule, I have no current. If I have no molecule, I still have heat. There's so much radiative heating between my substrate and my tip. So you have to control for all of those sources of heating between your substrate and your tip to measure the amount of heating going through your molecule. That's one problem. Second problem is the heat conductivity of these things is actually very bad. They're very bad thermal conductors. And so as far as I know, there's only one person trying to do these types of measurements, Pramod Reddy at the University of Michigan. He does everything in ultra vacuum at 4 Kelvin with custom temperature probes. And he, I think, is still quite far. The last I met him. So measuring thermoelectric current is easy, but measuring heat transfer is
Could there be molecules which, when you apply this external force and pull them, they undergo a conformational change so that you go from interfering to not?
Yeah, that would, we might have one. I don't know. We've designed many iterations. This is our dream. You apply a force, you break a bond, or you change the conformation, and you go from one system to another. I hope we find one, but
Does optical activity of a molecule has an effect on the molecular conductance? Like if you use one stereoisomer of a molecule, you get one conductance, and do you expect the change in the conductance if you use another stereoisomer of the molecule?
So based on this simple transmission picture that I have, just the chirality of the molecule is not going to affect the conductance. However, there are experiments where they've probed spin transport on long chains of chiral molecules, and then they see some dependence on the spin transport. But I'm not the best person to comment.
I have a question, Latha. So taking it to a next level, so these are gold contacts that you have. So now if we think of other kinds of applications, not just, looking at single molecule circuits, but now taking it further down the line for device applications, because these measurements are crucial at different backbones that you did, for example, which the data was not presented here, but how would one design experiments with different electrode contacts and in a sense try to exploit the richness of the conformational heterogeneity that exists in these molecules because of the flexibility? How would one go about designing certain things systematically? Because that's what, at a molecular level, for making these devices work with high efficiency, we need to have, of course, ballistic transport within the molecules, which certain polymers show, but also ballistic transport at the interface. So
yeah, so with gold we can achieve. So it's also ballistic at the interface.
Yeah. Yes, absolutely.
But you're probably thinking about higher transparency.
Right.
So with gold we can get that.
It's expensive for a device purpose.
Yeah. We can work. So our experiments are made primarily to learn how things work.
Yeah, sure.
And so, but we have experimented with platinum, which is even more expensive.
Yeah.
Silver.
Yeah.
And we haven't worked with anything else because our setup is all ambient. Because it's accessible to solutions, etc., right. And you need to be clean because if your substrate
contamination from the oxide layer. Yeah.
So that's one issue, but the conformations I think is really, that's again getting functionality of inherent properties that you don't have in silicon-based devices.
Right.
I think that's really
okay. Are there any more questions from college students? Okay, well, I will not put you on the spot, but if not, then let's thank Latha for this wonderful talk, and we hope it inspires some of you to do very fundamental level experiments.